beans, y'all. Let's keep working with integrable functions. First up, a starting theorem. Suppose f and g are two functions that are both integrable on the same interval. Okay, so f and g are integrable on the same interval ab. Then we're going to make a new function, which is just the sum, f plus g. And the theorem is, not only does the left side exist, not only is the left side integrable, but the value of this integral is exactly the same as the integral of f plus the integral of g. And this does bear a lot of similarity to things we've already proven. For example, limits of sequences. If two sequences have limits, then so does the sum sequence. Functions obey the same thing, derivatives obey the same thing, and now integrals. Yeah, well, I mean, there's a pattern to it, but we keep going. So the result is easier to prove using Riemann sums versus Darboux integrability. So first, for any positive epsilon, since f and g are both integrable, there are going to be two separate deltas, one for f and one for g, two positive deltas. So for any partition whose norm is less than either delta f or delta g, and for any choice of sampling points, okay, and for different partitions we get different sampling points, but the Riemann sum with respect to the partition whose norm is less than delta f, since f is integrable, if I make this partition sufficiently fine, this Riemann sum is very close to the value of this integral. But for a different partition which respects the delta that g required, this Riemann sum will be sufficiently close to the integral of g. So if I pick a partition whose norm is less than both, specifically if it's less than the smaller of the two deltas, for any choice of sampling points, we'll get both of the above inequalities. So then let's take a Riemann sum for one of these partitions whose norm is smaller than both delta f and delta g, and let's look at its Riemann sum. So since this sum has only finitely many terms, I can distribute this out, f of si delta xi, g of si delta xi, and if I collect all of the f of si's in one sum and all of the g of si's in one sum, we can write it like this. And that's just a Riemann sum of f plus a Riemann sum of g. Now we can apply the triangle inequality. So in the previous slide, we showed that the Riemann sum of f plus g is just the Riemann sum of f plus the Riemann sum of g. So I can just arrange terms, Riemann sum of f minus this integral, and then Riemann sum of g minus this integral. Use the triangle inequality. So this in absolute value is less than or equal to the sum of these two things. But since the partition had norm less than delta f, this is going to be small, and since the partition had norm less than delta g, this is also going to be small. So both of them are less than epsilon over 2. So not only did we show that f plus g is integrable, that there is some number that the Riemann sums are close to, the actual value is exactly what we expected, the integral of f plus the integral of g. And the sum law for derivatives also fell right out of the definition of the derivative, that's true. This is slightly more involved. The fundamental observation to make was that the Riemann sum of f plus g is just the Riemann sum of f plus the Riemann sum of g. But things are going to get a little worse, that's true. So here's a sample problem. Okay, suppose you have an integrable function f, then so is a constant times f. And similarly, not only is a constant times f also integrable, but the value of this integral, the constant can just factor out, and you get the constant times the integral of f. So this one's a little easier than the last one, but work through it using Riemann sums. Okay, hopefully you were able to finish this. For any epsilon u, there will be a delta that works for f. And if you simply replace delta with delta divided by the absolute value of c, then you'll get one that works for c times f. There's a little hiccup because you don't want to divide by 0, but if c is equal to 0, we just get a constant function and a 0 over here. Okay, moving on. So here's a useful result. Suppose we have an interval that goes from a to c. We've got a bounded function with supremum and infimum capital and little m. What we're going to do is we're going to pick a b somewhere in between a and c. This creates two intervals from a to b and then from b to c. On the left interval, a to b, we make supremum capital M sub L and infimum little m sub L. On the right interval from b to c, we use capital M sub R and little m sub R for the sup and inf on those pieces. Then we get two inequalities. Okay, so first we get this. Let's unpack what this is saying. The supremum overall times the length of the entire interval minus the sup on the left times the length of the left plus the sup on the right times the length on the right. So from the overall supremum times the overall width, I take away both the sup on the left times the length of the left and the sup of the right times the length of the right. This overall difference will be less than or equal to the difference between the sup and inf overall times the length of the interval overall. And a very similar inequality for infimums. Infimum overall times length overall. Take away left inf times left length, and also take away, because once you distribute this minus sign, also take away right inf times right length. That distance overall will also be less than or equal to the same thing. Okay, so here's a picture for what's going on. We've got our interval from A to C. We split it somewhere, okay, and I'm going to try to draw a reasonable-ish picture. Sure, here's our function f. So it looks like here is our sup overall. Now, if I try to see exactly where this line B is, it looks like this right here is the sup on the left, which means this is also the sup overall. Here is the inf overall, which also happens to be the inf on the left. And it looks like maybe this value here is the inf on the right. So let's go ahead and change up our colors. Okay. So M times C minus A is this entire rectangle, the supremum overall times the width of the entire thing. Then what I'm going to do is I'm going to subtract, and let's draw this in blue. I'm going to subtract the supremum on the left times the length of the left. That's going to be this rectangle right here. But I'm also going to subtract, and let's go ahead and do this in, I don't know, purple. I'm also going to subtract the sup on the right times the length of the right interval. That would be, whoops, that's the inf. That would be this right here. Okay, so when I take the green thing and I take away both the blue and the purple, the only thing that remains is, in this picture, a relatively small thing here. But the height of this thing can't be any bigger than the supremum overall. The thing that remains can't have anything that exists over the overall supremum, but it also can't have anything that exists under the overall infimum. Since I took away the left supremum and I took away the right supremum, I took away something bigger than the overall infimum on both sides. So the bit that remains cannot be any wider than the overall sup minus the overall inf, and it certainly can't be any longer than the entire interval from A to C. And that's the right-hand side of the inequality. Okay, and a very similar type of picture works for the second inequality that involved infs. So, okay, so here's another set of inequalities. So if you take the overall inf times the length of the interval, first you could say C minus A is simply equal to C minus B plus B minus A. So this would be equal to M, not M sub L, just little m times B minus A plus little m times C minus B. But the overall inf is less than or equal to the inf on the left, and it's also less than or equal to the inf on the right. That would give you this here. The inf on the left is less than or equal to the sup on the left. The inf on the right is less than or equal to the sup on the right. Then you would say the sup on the left is less than or equal to the overall sup. The sup on the right is less than or equal to the overall sup. Okay, so this can each be replaced with a less than or equal to capital M. Then you could collect them together and cancel out the b's and get here. So here is an overall set of inequalities that we have. Now consider taking any sample point S is anywhere from A to C, but x1 is specifically on the left and x2 is specifically on the right. So you'll also get an inequality just using sample points rather than sups and infs. So here's the picture again. We have A to C. We split it somewhere in the middle at B. We have our function. Okay. So here is our overall sup. Here is our overall inf. This is also equal to the inf on the left piece, but here is our sup on the right piece. And it looks like about here is our inf on the right, and this happens to also be the sup on the right. Okay, now what we do is we pick an arbitrary sample point. It's going to be on one of the two sides. I'm just going to pick it here. Here is our sample point S. x1 has to be from the left, and x2 has to be from the right. So f of x1 is this height. Notice that since x1 is on the left, that f of x1 has to be in between, sorry, I drew this as mr, that's of course ml. This is our left piece. So since x1 is on the left, the value f of x1 has to be in between the two ml's. And since x2 is on the right, the value f of x2 is in between the two mr's. Whereas the value f of s is simply in between the two m's, because it was somewhere in between a and c. So the value of the function at some point times the entire width, if I take away a value on the left times the length of the left plus the value on somewhere in the right times the length of the right, we'll get the same inequality here. And this really just follows because in the previous slide, this f of s, this f of x1, this f of x2 were just replaced with either overall suprema, suprema on the left, suprema on the right, or overall inf, inf on the left, inf on the right. And the value of our functions are going to be trapped somewhere between as well, so that we get a very similar geometric picture. So it does come across fairly straightforward. We've got the value of the function at some point times the overall width, and we're taking away two things here. And the worst that could happen would be to be left with the entire distance between the sup and the inf over the entire interval a to c. That's another way of thinking of this. Okay, if I take some big rectangle and I take out two intermediate rectangles, the worst thing that could be left would be as big a gap between two values of the function as possible across the entire interval from a to c. So said like that, it's a little more straightforward. But the fact that we're saying it so specifically and working through it does sort of suggest this is going to be an important observation. Okay, so here's a corollary to this. Suppose f is a bounded function on the interval from a to b. It's got overall supremum n, overall infimum m, as always. P is a partition and its norm is delta. We're going to refine P by adding a single point. So we add some point in between a and b, and we're calling that point y, and we make a new partition. So this partition P prime is simply the old partition P added 1 point. Then we get the lower sum of the old partition compared to the lower sum of the new partition. By adding a point to the partition, the lower sum actually gets bigger, whereas the upper sum can only get smaller. But how much did it get bigger? Not more than the distance between the sup and inf times delta, the norm of the partition. So notice this is the lower sum with respect to the original partition, and so is this. So the new partition has a larger lower sum, but how much larger was it? Not more than this quantity. Similarly, the upper sum for P prime got smaller, but not by more than the same quantity here. Okay, so the pieces of the two partitions are exactly the same. All we did was add 1 point. So the only difference between the two partitions is one interval has been broken into two pieces. So the pieces of the two partitions are almost exactly the same, but 1 point has been added. So what we've shown is that on that one interval, we can only decrease the upper sum or increase the lower sum because we have made a refinement. And we've already shown that refining partitions can only make upper sums smaller and lower sums bigger. And in fact, the most we can add or subtract by doing this refinement by 1 point is the length of the interval that was split times the difference between the sup and the inf. This was the result we just sort of showed. On the previous slide, it was A and C being split at an intermediate point B. But still, by adding a single point and looking either at Riemann sums or at upper and lower sums, the most the value can change is the difference between the sup and inf, that's our capital M minus little m, times the length of the interval. Now on the previous result, that was C minus A, but here the length of the interval is from our partition P, which is no larger than delta. So if we refine partitions by adding a single point, this tells us how much the upper and lower sums can possibly change. Adding a single point to a partition can only change the value of the upper and lower sums by, at most, the norm of the partition, delta, aka the biggest possible length that we split in two, times the biggest possible change in value in the function, and the biggest possible change in value in the function is the supremum minus the infimum. But if we have two completely different partitions, this isn't terribly useful. This tells us how we can go from one partition to another partition that has one point added. But if I just have two totally different partitions with perhaps no points in common, there's not a lot this does for us, that's true. So here is a surprisingly difficult theorem to prove. Suppose f is known to be integrable on the interval from a to b. Then I pick a c past b. So I take a new function, which is the same as f wherever f was defined, and then by extending from b all the way to c, I just force the function to be 0. So I had a function doing its thing from a to b, and then I just make it 0 a little while longer. If the original function was integrable, so is the new one, and the value of the integral is the same. Notice that this integral goes all the way to c, whereas this one only goes to b. F of x was only assumed to exist from a to b. I extend it by making it equal to f of x where f of x existed and making it 0 past that point. And we're saying the new function is integrable, and extending with this 0 doesn't even change the value of the integral. In terms of a picture, we say, here's a, here's b. F of x is integrable. It's nice, it's doing its thing. I then extend this. Let's go with green. So I pick a point C past B. I make a new function that's exactly the same, except past this point, it's just 0. And what we're saying is this new function, which was just the same as the old one, with this extension of 0, is still integrable, and the value of the integral hasn't changed. Geometrically, I agree it seems obvious. When I draw the picture, no one ever objects. But the proof is going to be a little ugly. So we assumed f was Riemann integrable on the interval from a to b. Therefore, if a partition is sufficiently fine, Riemann sums, upper sums, and lower sums are all going to be very close to the desired value, the integral from a to b of f. But a partition of a to c is not necessarily the same thing as a partition of a to b. If I partition the interval from a to c, there's no guarantee that I happened to pick b itself as a partition point. Therefore, I might not actually have a partition of a to b lying within my partition from a to c. People love to assume that if you partition from a all the way to c, you must have partitioned from a to b. That's not true, because remember, a partition has to contain both endpoints. And if I partition from a to c, there's no guarantee that I picked that endpoint b as one of my partition points. In terms of a picture, here's A, here's C, and here's B somewhere in between. If I make a partition from A to C, I might pick this point, this point, this point, this point, this point, this point, and this point. I partitioned from A to C. I did not partition from A to B because I have this interval, then this one, and then I go too far. So this is not a partition from A to B. And then I keep going. But if I want to turn this into a partition from A to B, what do I have to do? Add a single point. So here is where we're going to use these results we've been discussing about what happens when you add a single point to a partition. If you take a partition from A to C, you may have to add a single point to get a partition from A to B and also a partition from B to C. Yes, so this is why we need to relate partitions of the big interval to integrability on the small interval. On the smaller interval from A to B, since f is integrable, we're going to know that Riemann sums on the left bit can be made close to the value we want. So since f is integrable on this interval from A to B, it must be bounded. And since f of x is 0 on the right bit, it's definitely bounded overall. So let capital M and little m be the sup and inf of the function on the big interval from A to C. It was bounded to begin with from A to B. We extend it by a constant, so it's still bounded. So let epsilon be positive, then there must be some delta, so that if I have a partition of the left interval whose norm is less than delta, then using the function f, the upper sum minus the desired value is less than epsilon over 3. Because f is integrable, if I make the partition sufficiently fine, the upper sum will be as close as I want to the value of the integral. And there's an epsilon over 3 here, which does suggest this is going to go on in 3 parts. Yeah. So now, let P be any partition of the entire thing whose norm is less than this same delta. We're also going to require it to be smaller than this quantity, epsilon over 3 times the quantity big M minus little m. Set that aside for the moment. So delta is small enough to work on the left for the function f, but also smaller than this quantity. Now, since the partition we made might not contain B itself, so it might not contain as a subset a partition from A to B, we're going to refine it by adding that point. Now, what we have shown is by adding a point to a partition, the upper and lower sums change by no more than the difference between the sup and inf times the norm of the partition. But delta was chosen to be less than this, so that m minus m is going to cancel out. So by adding a single point to the partition, upper and lower sums change by no more than epsilon over 3. So the upper and lower sums of f bar for the partition P prime, this is the one that included the point B, can be split into 2 sums. First, go from A to B, then go from B to C. Okay, we took the partition P, we added a single point, and we're basically saying go up to this point B, then as a separate step, finish up the sum. So the first is a partition from A to B, so all my sample points are in between A and B. So the upper sum, which doesn't need sample points, sorry, the upper sum is within epsilon over 3 of the desired value. Since I refined the partition, I only made the norm smaller. So since the original partition was sufficiently fine to give upper sums for f within epsilon over 3 of the desired value L, so is the new partition. Okay. Now on the interval from B to C, what happens? No, we're not done yet, sorry. Nope. So the upper and lower sums of f on the interval B to C are all very, very close to 0, okay? Because the function was 0 from B to C, except perhaps exactly at the point B, okay? The function f bar was f of x from A to B, including at B. So on this interval from B to C, I have a partition, and I may have chosen the left endpoint of the first partition piece. So every piece of the upper and lower sums and any Riemann sums would all be 0 except maybe the first one. Okay, the first one, the supremum can't, however, be larger than the overall supremum, and the infimum can't be smaller than the overall infimum. So the upper sum, all the pieces in the upper sum are 0 except maybe the first one, and that's going to give me nothing worse than an overall supremum times the biggest possible interval length of the partition, big M times delta, and the lower sum, every piece is 0 except maybe the first, and that can't be anything smaller than the overall infimum times the length, times the norm of the partition, the longest possible length in the partition. So if I choose delta to be really, really small, I can make both this and this, big M delta and little m times delta. I can make both of them less than epsilon over 3. So for any partition of A to C which is sufficiently fine, 3 different things happen now. We refine the partition by adding B. The upper and lower sums can only change by epsilon over 3. The upper and lower sums on the left are forced to be within epsilon over 3 of the desired integral value because f was integrable, and we chose our partition to be sufficiently fine to make this happen. And the upper and lower sums on the right are less than epsilon over 3 in absolute value because all the pieces were 0 except at most 1. And we chose delta to be sufficiently small to make this happen. So our overall partition has been changed by at most epsilon over 3 by adding a point. After this change, the upper and lower sum on the left are within epsilon over 3 of the desired value, and the upper and lower sums on the right are no more than epsilon over 3 in total. So, thankfully, yes, we are ready to finish the proof of this result. Overall, the upper and lower sums are within epsilon of the desired value of the integral of f. So what we have is, yes, if I go all the way from a to c and integrate f bar, I'll get the same value as if I had just been integrating f from a to b. We got upper and lower sums from a to b, very close to this value. From b to c, the function was almost entirely 0, and one piece of the partition can't change things very much, as long as the norm of the partition is sufficiently small. And we did have to add a single spot to the partition so that we could actually split from A to B and then from B to C. But changing a partition by adding one piece does not change the value very much. And that's how we put this all together. And that is a fairly complicated proof for something that makes so much intuitive sense. If you extend a function by making it 0 past a certain point, you don't change whether or not it's integrable, and you also don't change the value of the integral. But now that we have that behind us and that is proved, try to work on the following that are all fairly similar. However, you can use the previous result to prove these. So just a few comments on these problems. So this first one said, if you have a function that's integrable, f of x, and you change the value at one point, not only do you not change the fact that the function is integrable, you don't change the value of the integral. So if you change the value of the function at one point, how much can that possibly throw off your upper and lower or possibly Riemann sums? Not very much. A single point can be chosen at most twice as a sampling point, and it can throw off at most 2 terms of your upper and lower sums. Because it could be a possible suit on 2 different intervals if it happens to have been chosen as one of the points of the partition. But 2 pieces out of the partition, or at most 2 pieces of the Riemann sum, is not a big difference as long as the widths that you're multiplying by are sufficiently small. So once you get that changing it at a single point can't do very much, you can do an inductive proof and get that changing it at finitely many points doesn't do much of anything. You don't have to do this inductively, it's just one possible way. And then these last ones are about constructing examples that do certain things that show if you change it at infinitely many points, things are not quite so easy. If you change the value of a function at infinitely many points, you might still be integrable with the same value, or you might just not be integrable anymore. You could, by changing the value at infinitely many points, you may have done a whole lot of bad stuff. And now what we can do is we can say, suppose f is integrable on 2 intervals, a to b and also b to c. Then I can glue these 2 things together and say that f is integrable from a to c, and in fact, the value of the overall integral is just the sum of the 2 pieces. This is something we learned back in Calc 1, and we get really used to gluing these regions together. And the only difference now is we have to worry about whether functions are even integrable. The good news, however, is that this is not nearly as bad as the last thing we proved. So what we're going to do is we're going to define 2 separate functions. F sub L is f of x on the left bit and then extended to be 0, and f sub r is f of x on the right bit and left extended to be 0. And we already know that since f of x is integrable here, fl is integrable overall. Similarly, since fx is integrable here, fr is integrable overall. We've already proven that. So here's a picture. If this is my function f of x, all the way from a to b to c, and we know we're integrable on the left and we're integrable on the right. That's part of our givens. Okay, we're trying to just glue this together. So we define f sub L to do this. It's equal to f on the left, and then it's 0. And then I also define f sub r to be 0 on the left, but then the value of the function on the right. So since we were known to be integrable on the left, the green function overall is integrable. And since we were known to be integrable on the right, the blue function overall is integrable. Also, the integral of the green function is just this left integral, and the integral of the blue function is just this right one. But what's the very first thing we proved today? But this isn't going to go on forever, I swear. We are really almost done with this already. So FL and FR are both integrable, and therefore the value of the integral is the same as the value of f on the left bit or the value of f on the right bit. We're just relying on that nasty theorem that we've already completed a proof of. If I take an integrable function and extend it to be 0, either extending to the right or similarly extending to the left, you don't change the value. But the value of the function is exactly the sum of these two things, except possibly at the one point where we kind of shared what they were doing. Changing the value of a function at a single point, as one of your practice problems showed, does not affect whether it's integrable or not, nor does it affect the value of the integral. So basically, by changing it at a single point, we're not going to change much, so we can just say the function f is just fl plus fr. On the left, this gives me f and this gives me 0. But on the right bit, this gives me f and this gives me 0. So regardless, the function overall is its left half plus its right half. Since FL and FR are known to be integrable, so is the sum, and the value of this integral is the sum of these two integrals. But this integral is that bit, and the right integral was that one. And so we're done. If I integrate from a to c f of x is equal to FL plus FR. The sum of two integrable functions is integrable, and the value can be computed by doing the integral from a to c of FL, but the integral from a to c of FL is just the integral from a to b of f, plus the integral from a to c of FR, but the integral from a to c of FR is just the integral from b to c of f. And we have it. If you want to integrate from a to c f of x, integrate from a to b, and then add on integrating from b to c. But to repeat, we needed to know to begin with that each of these integrals existed. You can take two existing regions and glue them together. What we don't yet know is if the left side exists, are we guaranteed to be able to split it up into two pieces like that? We have not addressed that problem yet. The givens here were if both pieces on the right side here, if both of these integrals exist. Then you can add them together and get that. Okay, so come on back next time and we keep talking about integrals.